Hello, good morning, everyone. Good evening, everyone, to 11th session of problem solving sessions. And today we will cover problems based on week 11 content, that is the second order systems response. So let's start with it. So the first question over here, it is a second order, it is a parallel RLC network, and the differential equation governing this parallel RLC network is given in the question, and we need to find out the damping factor, that is zeta, the natural frequency, that is omega n, the quality factor, and the type of the system. So let's start it. So now you can see that to this parallel RLC network, there is a source current that is being supplied. And if you apply KCL at this particular node, you will get that the current that is flowing in the node, that is so the current that is flowing out of the node is V naught by R plus the inductor's current plus the capacitor's current, and that is equal to the source current that is being supplied to the node. So the inductor's current IL can be written as now the V naught is common for all the three elements, as the three elements are in parallel. So the inductor current can be written as 1 by L integration of V naught dt, and the capacitor current can be written as C dV naught by dt. So if we put these quantities in the above equation, we get V naught by R plus 1 by L V naught dt, 1 by L integration of V naught dt plus C dV naught dt is equal to Is. So if we differentiate both the sides, we get C dV. So this term, after differentiating one more time, it becomes C d square V naught by dt square, plus now this term over here becomes 1 by R dV naught by dt, and since this was already an integral, after differentiation we get V naught 1 by L times V naught is equal to dis by dt. Now since the governing equation of any system is independent of the input, so if we have no input, that is for example we can put is equal to 0. In that case we get dv naught square by dv naught square d square v naught by dt square plus 1 by rc times dv naught by dt plus v naught by lc equals to 0. So if we compare it with the standard equation, that is we have this one, the natural frequency omega naught or omega n we get as 1 by root lc, and the and then this 2 zeta omega n now v is equal to 1 by rc. So from there we get value of zeta, the damping factor, as 1 by 2r times root L by C. Now for the given values of inductor, capacitor, and resistor, so the value of resistor over here has been given as 10 ohms. So for these given values, we get zeta. If we substitute the values of a 1 microhenry inductor, 10 nanofarad capacitor, and a 10 ohm resistor, we get the damping factor as 0.5. And for the systems with damping factor less than 1, we get an underdamped system. So this is an underdamped system. Now the omega n, that is the natural frequency 1 by root LC, comes out to be 10 megaradian per second, and the quality factor, that is 1 by 2 zeta, that comes out to be that the equation for that is R root under C by L, and since zeta is 0.5, so quality factor comes out to be 1. Now what are underdamped, critically damped, and overdamped system? So for zeta less than 1 and quality factor greater than 0.5, we have underdamped system. For zeta equal to 1 and quality factor equal to the quality factor equal to 0.5, we have a critically damped system. And for the zeta greater than 1 and quality factor less than 0.5, we have overdamped system. So if you look at the step responses of these kind of systems, so what you get, so this curve over here represents a overdamped system. This curve somewhere over here represents a critically damped system, and when you start seeing ringing in the response, that is an underdamped system. So in this direction, as we move, the quality factor starts increasing and zeta starts reducing. Now, for a quality factor of infinite and zeta equal to zero, what we will see a sinusoidal curve with no damping at all. So now, in terms of poles and zero, how uh, da- uh, these systems look. So from the auxiliary equation of the differential equation, that is d square plus 2 zeta 2 omega n zeta d plus omega n square, we can replace the d in the auxiliary equation by the Laplace variable s, that is equal to sigma plus j omega. So if we represent this in on the s plane, the complex plane, what we get is the following. For zeta less than 1, the poles, the zeros of the auxiliary equation looks like this. That is minus omega n zeta plus minus j omega n into root under 1 minus zeta square. And since zeta is less than 1, this quantity is real and this complete quantity is complex. So the poles are complex conjugate of each other. Now for a constant value of omega n, these poles will lie on this circle whose radius is equal to omega n. And for zeta equal to 1, this term will go to 0 and we will have two poles coinciding at omega and zeta, and since zeta equal to 1, so this also lies on the same radius. And for after that, for zeta greater than 1, the poles comes on the real axis and the poles become real. So the value of these poles are omega minus omega and zeta plus minus omega n times root under zeta square minus 1. Now since zeta square is greater than 1, this quantity is real and this complete quantity is also real. So in this, for the underdamped system, if you want to find out the zeta, so you can find the angle between the negative real axis and the first pole, and that angle is basically cos inverse of zeta. So from there you can locate the you can find the value of damping factor from the pole zero location. And other interesting thing that can be observed is you see in case of overdamped system, the poles of the the poles of the system are basically their geometric mean lies at omega n. So if you try to find its geometric mean, you will get omega n zeta square whole square plus, sorry, minus of omega n zeta whole square minus omega n squares root under. So this comes out to be omega n. So when the poles are real, their geometric mean is equal to the value zeta. So these are all things you should keep in mind while dealing with second order systems. So now let's move to the next question. Now again, you have the same system. In this case, it is asked that for a critical damp system, what will be the value of R, omega, and Q? You have been given the values of L and C. So critically damped system, that means zeta equal to 1. And if you have zeta equal to 1, you from the expression of zeta that we found in previous question, we can substitute the value of L and C as 1 microhenry and 10 nanofarad. And if we substitute that, the value of resistance we get as 5 ohms. So for 5 ohm resistance, we can get a critically damped system. Now the omega n will be 1 upon root LC, and that still comes as 10 mega radian per second, as we saw in the previous example. So as we see in this curve, so if we change the damping factor by changing the resistance, the zeta doesn't, the omega n doesn't changes. So that remains the same, and quality factor, that is 1 upon 2 zeta, is equal to zero point 0.5. So this is how you need to solve that question. Now let's move to another question. So in this, the circuit, so now in this question, this is slightly different from the previous one. So it was, the previous question was a completely parallel RLC network. In this, it's neither a series RLC nor a parallel RLC. It's a little complicated network. So, like in parallel RLC or series RLC, you can by heart the values of the damping factor, the omega n, and the quality factor. However, in case of complex networks, you need to find out the differential equation and then compare its coefficient with the standard differential equation of a second order system. So this is what is we are going to do in this question. So let's see, work it out. Now the now in this question, again, you will apply KVL in this loop. So first of all, you have V naught across the capacitor and resistor that are in parallel. So the current that is flowing through this loop and this parallel resistor capacitor combination is equal to the sum of current that is flowing in resistor and that is flowing in capacitor. Now, the current flowing in resistor is straightforward, that is V naught by R. And since V naught is the voltage developed across the capacitor, the current flowing through it is C dV naught by dt. So the total current flowing inside this resistor capacitor parallel combination is V naught by R plus C dV naught by dt. Now, if you apply KVL in this loop, so you get Vs minus IR. So since both the resistance are equal, so I have denoted both of them as R. So Vs minus IR minus, now since through an inductor I current is flowing, and we know that VL is equal to LdI by dt. So that is basically I have substituted over here. So V naught minus IR minus LdI by dt is again, sorry, Vs minus IR minus LdI by dt is equal to V naught. Now, if we substitute the value of I into the this equation, so we get the following expression, that is V naught by R plus C dV naught by dt times R plus L d by dt of I. Now, what is the value of I? That is V naught by R plus C dV naught by dt, and then finally plus V naught. So I have taken these two terms on the RHS, and that's how I get it. So now if we simplify it, so this particular this term when multiplied with this term, so it will become double differentiation. So it's LC dV square dV naught square by dt square plus the single differential terms are the come from the following places. So one is this one that gives the coefficient of RC, and the other is this one that gives the coefficient of L by R. And the zeroth differential is basically, so this R and R gets cancelled. So one V naught from here, other V naught from here. So it comes out to be 2 V naught is equal to Vs. So now if we take this term to divide the complete equation by LC, we get d square V naught by dt square plus, now if LC is divided by here, this CC cancel though, so this gives you R by L plus 1 by RC times dV naught by dt plus 2 by LC times V naught is equal to Vs by LC. So from here we get omega, the value of omega n. So from this case, we get value of omega n as root under 2 by LC. And now if we compare this term with the standard equation of with the standard coefficient of first order derivatives, that is 2 zeta omega n, and place the value of omega n from here. So 2 zeta times omega n is equal to r by l plus 1 by rc. So from there we get the value of zeta as 1 by 2 root 2 into r times root c by l plus 1 by r times root l by c. So this is how you needed to find the values of zeta and omega in this question. Now to find the numerical values, the values of the resistor, inductor and capacitor is given. So you can substitute these numerical values in the equation. So from there, the value of inductance is given as 2 microhenry. So this comes out to be 2 upon 2 microhenry into 10 nanofarad of capacitor, and that gives you 10 megaradian per second. And zeta, that is 1 by 2 root 2 times r times root times root c by l plus 1 by r times root l by c. So substitute the value of l and c and r again. So from there you get zeta as 2.3. So this is a overdamped system. Okay. So in this case, you can see if this resistor goes to 0, then you have a series RLC network. In that case, your coefficient of your zeta will become, mm, in that case, so if this resistor goes to 0, you have a series RLC network. And if this resistor goes to, sorry, if this resistor goes to infinite, you have a series RLC network. And if this resistor goes to 0, you have a parallel RLC network. So this you can observe. So basically, for achieving a high quality factor, you need to increase this value of resistance and reduce this value of resistance. So this is what you can keep in mind. Okay, so let's move forward. Now again you have a series RLC this time. So in this case, again you need to find the value of omega, zeta, omega, and q. So for series RLC, again we will apply KVL in this loop. So now the current that is flowing, I that is flowing inside the capacitor. So let's call that some value I, and that is the same current that is flowing across the loop. Now I is equal to C dV naught by dt. So if you apply the KVL in this loop, you get Vs is equal to R times I plus uh, L di by dt plus V naught. So L di by dt is voltage developed across inductor. I times R is the voltage developed across the resistor, and V naught is the voltage developed across the capacitor. Now, substituting the value of I over here and here, you get C dV naught by dt plus L d square V naught by dt square plus V naught is equal to Vs. So again, substitute, so put Vs as 0 for time being. So what you get over here is R times, sorry, um, LDI by dt. So I times R plus LdI by dt plus V naught is equal to 0. So from there you get the value of just a minute. Oh, sorry. Here it will be CL times d square V naught by dt square. So from here, what you get is d square V naught by dt square plus here you get R by L d, dv naught by dt plus V naught by LC is equal to 0. And if you compare it with d square V naught by dt square plus 2 zeta omega n dv naught by dt plus V naught times omega n square is equal to 0. So omega n you get as 1 by root LC and 2 zeta omega n. So omega n you substitute as 1 by root LC is equal to R by L. That means zeta is equal to R by 2 root C by L. So in this case, you observe that the as this resistor increases, your damping increases and your quality factor reduces. And in case of parallel RLC network, what we saw was uh, damping coefficient was opposite of this. So it was 1 by 2R times root L by C. In this case, the damping factor was this. So in this case, you need an infinite resistance so that damping is 0. And in this case, in series RLC case, you need a 0 resistance to make the damping 0. So these things you can keep in mind, and you can also keep in mind the values of the damping factor, quality factor, and the natural frequency for both the R series and parallel RLC network for quick calculations. Now, so let's move to the next question. Now, again, this question has two sources. And this case, again, you have to find the values of zeta, omega naught, and q. So what you need to do now is, again, the same thing. So first of all, we'll solve it with traditional way, and then we will see like uh, what insights we can decipher from this. Now, uh, let's take this as one node. So let's call this as, say, V naught. So what we have is V naught. So the current that is flowing in the resistor and the inductor is overall V naught C dV naught by dt plus, now the V naught is given, and the current through the inductor for a voltage V naught is 1 by L times integration of V naught dt, and the current that is flowing in this direction is plus V naught minus Vs by R. Now this complete current is being supplied by this current source. So this is equal to Is. Okay. So what we have now is 1 by L V naught dt plus C dV naught by dt plus V naught by R is equal to Is plus Vs by R. So now differentiating both LHS and RHS with respect to time, we get C dV naught, sorry, C d square V naught by dt square plus dV naught by dt times 1 by R plus V naught by L equal to dis by dt plus 1 by R times dvs by dt. So now, if you if you again divide everything by c, so you get dv square, dv naught square by dt square plus 1 by rc dv naught by dt plus v naught by lc is equal to 1 by c times dis by dt plus 1 by rc times dvs by dt. So these are the input uh, uh, these are the way the input will affect the system, and this is the natural response of the system irrespective of the input. So from here you can get the values of omega n, that comes out to be 1 by root lc, and zeta, that comes out to be 1 by 2 times, so r root l by c. So these are the values of omega and zeta, and omega and zeta. Now these are the values that you get for a parallel RLC network. Now if you see how this is a parallel RLC network, so in this case what you need to do, you need to de-energize all the sources and then see what kind of network is it. So if you de-energize the voltage source, it becomes a short circuit. If you de-energize the current source, it becomes an open circuit. So the uh, network looks something like this. You have an R, a C in parallel to it, then an inductor, and then one more C. Let's call it C1, but this is not connected to anything. This is an open circuit, so this doesn't affect the system. So you can see this is a parallel RLC network, and this C over here of 50 picofarads is redundant. So this is how you needed to solve this question. Now, in this question, we are given that so this is a network, and in this case, you are given that Vs has Vs is a form cos omega naught t, and you need to find out the steady state value of IR, IR in steady state. So you can see Vs is given as cos 10 to the power 8t. So this has been given at time t equal to say minus infinity, in at which all the transients have died. Now, if the transients have died and the system is in steady state with a sinusoidal input, so to analyze this kind of system, we use a frequency response method. So in that, the impedance of the inductance becomes SL, where S is replaced by j omega. So impedance becomes j omega L for the inductance, and the impedance becomes for capacitance becomes 1 upon j omega C. So if we substitute these values over here, what we get here is Vs. So this is now now since both the inductors have same value, so let's call both of them as L, the capacitor as C, and the resistor as R. So what we get over here is an inductor L, a voltage source Vs, then a capacitor, now a resistor over here, and an inductor L. So let's call it j omega L 1 upon j omega C, and again it's j times omega L. So the value of the looking in impedance from this node comes out to be the parallel combination of the three. So let's call it Z1 by ZEQ. So that comes out to be 1 by R plus 1 by j omega L plus 1 by 1 upon j omega C. So that comes out to be 1 by R plus 1 by j omega L plus j omega LC, j omega C. So let's take this to the next page. So now the value of so this impedance becomes R times j omega L, and if we put the numerator, so that becomes j omega L plus R plus, sorry, minus omega square times LC. So Z equivalent we get as j omega L times R upon j omega L plus R minus omega square LC. Yeah, correct. So in these kind of cases, you can always do a sanity check to check whether whatever result you have got is correct or not. So for the sanity check, what you see is what you can do here is the dimensional analysis. Now for dimensional analysis, the dimension of this should be in ohms. Now since j omega L is an impedance that will have its value as ohms, R is again also an impedance. So in the numerator you have impedance squared, and now in denominator you have impedance, and this is omega square LC. Now what is this? This is s square times LC. So if we have j omega as s, so you get s square times LC. So what is it? This is s times L times s times C. So sorry, here one you will have R also. So see, this was the mistake that I committed over here, and that got caught up in the sanity check. So now what you have is omega square LC is a dimensionless quantity, because we know that 1 by root LC is omega naught. So uh, one so LC will have the dimensions that are of frequencies minus 2, and since you have frequency square over here, so this is a dimensionless quantity, and then you have R. So we have impedance square in the numerator, impedance in the denominator. So overall this has a dimension of ohms, that is impedance, and that's we want. So we have done the sanity check, and this passes the equation, the expression we derived passes that. Now what we have is j omega L. So we have Vs over here, and over here we have the equivalent resistance Zeq. So now if now Vs, so this V naught over here, let's call this V naught. So V naught will be Zeq by j omega L plus Zeq. So Zeq's value you can put from the above equation. So that this becomes j omega L times R upon j omega L plus R minus omega square LC times R times j omega L plus the same thing again, j omega L times R plus divided by j omega L plus R minus omega square LC times R. Okay, so now we have j omega L times R divided by j omega L times j omega L plus R minus omega square LCR plus j omega L times R. Now this j omega L we have common in numerators and denominators, so this can be cancelled. So on doing that, we get, so let's again take it to the new page. So finally we get the value as r upon j omega l plus r minus omega square lcr. Now if we to take r also at the bottom, we get 1 upon minus omega square lc plus j omega l by r plus 1. So again, the sanity check. So all are dimensionless quantities. Omega square Lc is a dimensionless quantity. J omega L, which is an impedance, divided by R, which is again an impedance, is again a dimensionless quantity, and one again is a dimensionless quantity. So this complete equation is a dimensionless quantity, and since it's a ratio of the input voltage and the voltage V out, so this has to be a dimensionless quantity, so it's correct. Now what we needed to find over here is I by this IR. So the voltage at this point we know that is V naught, so we need to find now the value of IR, and that comes out to be so IR of j omega is equal to Vs of j omega times 1 by R into the denominator equation, that is minus omega square Lc plus j omega L by R plus 1. Okay, now we need to find the magnitude and phase of so now since Vs is a sinusoidal function, that is cos 10 to the power 8 times t. So for omega equal to 10 to the power 8, we need to find the magnitude and phase response of the transfer function. So what transfer function we have over here? The h, or since it's a uh, transfer function from voltage to resistance, so voltage to current, so let's call it transconductance transfer function. So g of j omega is equal to 1 by r times minus omega square lc plus j omega l by r plus 1. So now uh, the magnitude of this transfer function will be equal to 1 by r times the square root of imaginary part square plus real part square. So that comes out to be 1 minus omega square lc times whole square plus omega square l square by r square. So this is the magnitude. And what is the phase? The phase of a system, phase of a pole, that you can calculate by, so phase of g of j omega. So now since the complex term is in denominator, so you have a minus of tan inverse of coefficient of real part, the imaginary part, that is omega L by R, divided by the real part, that is 1 minus omega square LC. So these two equations you have. Now we substitute the value of LCR and omega to find out the magnitude and phase shift in the current equation. So what we have now is, now again let's paste this result that we got. So we have this result. The value of omega is 10 to the power 8. The value of resistance is 100 ohms. L is 200 nanohenry and capacitor is 1 nanofarad. So R equal to 100 ohms, L equal to 200 nanohenry, and C is equal to 1 nanofarad. So just a minute. I think there is a mistake in the calculation. Just let me check once. So yeah, you have here here you have it as, so j omega l you have twice. So what you have over here is 2 j omega l and not j omega l. So here it comes as 2, then here 2, 2. Hmm. Uh, Sorry, it's not 2 j omega l, it's 2 r. I'm sorry for the. So what you have over here is 2r. So here also you have 2r and LC by 2. Sorry, and at the out also you have. So let's uh, okay. So let's do it once again. Let's see where is the mistake in this. Now, why I think there is a mistake? The reason is that from here, if you compare the value of the natural frequency from this, you obtain it as 1 by root of LC. However, in the circuit, if you see it, so if you de-energize this voltage source to 0, you get this inductor and this inductor in parallel to each other. So their equivalent capacitance inductance becomes L by 2. So the natural frequency that you should have obtained should have been 2 by root over LC. However, since I'm obtaining only 1 by root over LC, so I feel there is a mistake in question. So my point is that you need to be careful while so this is algebra, and algebra can so complex algebra can have mistakes in them, but if you are careful enough to see whatever results you are getting are correct intuitively, then you can you can figure out these mistakes. So let's try to figure out the mistake in this. So let's start it from the equivalent impedance. So that is 1 by r plus 1 by j omega l plus j omega c. So this is correct. Then we have this as the equivalent resistance comes out to be j omega l times r upon j omega l plus r minus omega square LCR. This also is correct. Now you have so z equivalent upon so let's write it in this form. So I have divided both numerator and denominator by resistance. So I get this as the equivalent inductance, equivalent impedance. So over here again, we do the same thing, and we get this. And here also the we divide both numerator and denominator by the resistance. So we get the value as, So now if we expand the equation, what we have is what we have over here is j omega L divided by, now again this j omega L can be cancelled in top and bottom. So what we have is, so if we cancel that, we get 1 upon j omega L by R plus 1 minus omega square LC plus 1. So ultimately we get this as the equation of input and output voltage minus omega square LC plus j omega L by R plus 1. Sorry, plus 2. Now, this can be written as 1 0.5 divided by minus omega square LC by 2 plus j omega L by 2R plus 1. Now let's see whether this time we have got this correct or not. So for that, what we can do is we can run again a sanity check as to why this transfer function makes sense. So let's uh, remove this part, and so if we draw the circuit over here, we have L, R, L and C, right? And here we have Vs, and this we have called as V naught. So, and the expression that we have derived for the transfer function from Vs to V naught, that is that is basically 0.5 divided by minus omega square Lc by 2 plus j omega L by 2R plus 1. Okay. Now at DC, that is when omega equal to 0, so this is V naught by Vs. So at omega equal to 0, what we should get, the inductance impedance will be the smallest. Now, if the inductance is almost short circuit, so the value of resistance and the capacitance impedance anyways is infinite. The value of resistance also will be very huge as compared to the inductance impedance. So in this case, so now one common mistake. So let's say we need to find it intuitively at what must be the transfer function at DC. So wait, let me push this to next page. So if we need to find out intuitively what must be transfer function from Vs to V naught at DC, so what one might do is uh, the common knowledge says that we short the inductance and we open the resistance, open the impedance, and find out, work out the KCL and KVL to find out the value at DC. So if we try to do that, what happens? Let's see. So we have Vs over here. This is short circuited. We have a resistance R. Then there is a short circuit due to next inductor, and then there is an open circuit. Now, if you look over here, what you finally observe is you have a zero voltage over here and zero voltage connect this ground directly connected to the voltage source. This violates your KVL, that is the Kirchhoff's voltage law. So what is the problem that we are facing over here is that we cannot outrightly say that the impedance is a short circuit. The impedance will be close to short circuit, but then we need to see that the the source impedance is also almost zero. So this is also going to the impedance over here is also almost going to zero. The impedance over here is also almost going to zero. And if this impedance is very small, then this resistor can be neglected. So what we have as our final circuit is an inductor and an inductor. So in this case, since both the impedance are almost approaching zero, so their ratio, the impedance divider ratio won't in that. Basically, what you will have ultimately is j omega L divided by j omega L plus j omega L. So this omega will be cancelled, and what you will be left with is L upon L plus L. That means this will be just an inductance divider. So now, since both the inductance are equal, so the voltage that you get over here is half of what you have applied at the input. So with this, you can say that this point 0.5 makes sense, because from there also you get the value of V naught by Vs as 0.5. So you must keep in mind that while making these approximations of short circuit inductance and open circuit capacitance, you are not violating the basic KCL and KVL laws. And if you are seeing that this is happening, then you must see that okay, what mistake that you are making. So in this case, the mistake was that the source impedance and the load impedance both are approaching zero, so you cannot compare one with another, because since the both impedance are small, so their values are comparable. So resistor divider or impedance divider still holds. So now let's proceed further in this question. Now, since we have V naught by Vs, what we need to find now is the current, that is zero point 0.5 by R divided by, so IR by Vs comes out to be 0.5 by R divided by minus omega square LC by 2 plus j omega L by 2R plus 1. So this is what you have finally. Now, the natural frequency of this is, so the omega that has been given to you is 10 to the power 10 in the question. Now let's find out the natural frequency of this system. So this comes out to be root under 2 by LC. Now what are the value of L and C? So L is 200 nanohenry and capacitance is 1 nanofarad. If you substitute this, so what you get over here is omega n as 2 upon 200 into 10 to the power 9 minus 9 into 10 to the power minus 9. So this comes out to be omega n comes out to be 10 to the power 8. So you see that your natural frequency and input frequency are same. So the circuit will be in resonance. And since the circuit is in resonance, so what you will have ultimately is the following. So the circuit is in resonance. So what you have is IR by Vs at omega equal to 10 to the power 8. So this quantity goes to 1, sorry, minus 1, and this gets cancelled by the other quantity. So uh, ultimately you have the following thing. So zero point 0.5 by R times j omega L times R. So this is 0.5 upon j omega L is the final value of current that flows inside this uh, system. So the if you substitute the values, what you get is 0.5 upon, So it's point 0.5 upon j into 10 to the power 8 times 200 into 10 to the power minus 9. So this comes out to be point 0.5 upon j20. So 0.025 by j. Now this is 25 milliamps. Now the magnitude of IR comes out to be 25 milliamps, and the phase shift in the IR, that comes out to be minus of minus of pi by 2, because this j adds an additional phase of pi by 2. So this was it from my side. uh, these were the questions for today's practice session. So yeah, thank you for attending.